All right, we're good. So welding processes in which we mean to consume the electrode. And I'm going to start by those in which the electrode is consumed, but still without involving fluxes, just a shielding gas. So here we have gas metal arc welding. And if you remember when I showed you a lot of acronyms last class, I said, funny enough, you're going to remember them all and know what they mean. And you get to see what of these million of acronyms, and we've been talking so much about it. Gas metal arc welding, that's our official name, but typically I say MIG, and most people say MIG. Now, in Europe, the official name is MIG, but they're quirky, and they say that sometimes you should say MAG. I'll tell you this in a second, but when I say MIG, I'm talking about what the Europeans might call MIG, or sometimes about what the Europeans might call MAG. So, MIG. Here we have the base plate. Here we have the electrode. Here we have a shielding cup or a nozzle. And here we have, which I haven't marked it here, but we have the shielding gas coming out of the cup. So far, I described TIG. It's exactly the same. Now let me tell you the one difference that makes a world of difference, and in practice, the two processes look like nothing like each other. But so far, it's kind of the same. The difference is that in TIG, we have a tungsten electrode that we did not want to melt. That's why we called it non-consumable. But in MIG, we have a metal electrode we mean to consume. If we're welding steel, typically the electrode is steel. If we weld aluminum, typically the electrode is aluminum. But if the electrode consumes, how do I prevent the weld from stopping? Okay, what I do is I start to unspool a roll of wire, and the wire comes in and melts and falls in the form of droplets, and it makes the weld. So to some extent, it's kind of same as TIG gone wrong, in which we're melting the electrode, right? But now we do it under very good control. Now, if my electrode is unspooling and melting, I have an interesting problem of how do I make an electric circuit with something that is melting? So what we have is a sliding electrical contact, the same type we discussed in hot wire TIG, right? In which the hot wire was coming in and going through a sliding contact. And this we call the contact tip, which is this part here. So electricity comes into this contact tip that is made out of copper, gives the electricity to the wire, and then the electricity goes through this part of the wire and then jumps into the arc. So here the naming convention matters. And we're gonna use a particular naming convention for this class, which I think is a good one. But please know that people use the same words for different things. For example, we already discussed, if this is the arc, I'm going to call the length of the arc length. Sounds like trivial, and I said it kind of funny, but some people would define the arc length as other things. For example, the distance from the plate to the nozzle, but it makes no sense for us. So arc length is the length of the arc. Then the part of the electrode that is sticking outside the contact tip, so the current comes more or less at this point, right at the edge of the contact tip. And then the current circulates through this piece of wire. This piece of wire, we're gonna call it the electrode extension. It makes sense to me. However, our Bible, the procedure handbook, calls electrode extension the distance from the contact tip to the plate. So in this class and in exams, electrode extension is going to mean this extension. But we have to keep in mind that other people, like in the procedure handbook, say that electrode extension is something else. That something else we're going to call contact tip to workpiece distance, CTWD. Many people call it that way. I didn't invent it, right? And there is a difference between the CTWD and the electrode extension. The only time in which CTWD and electrode extension would be the same for us is if we have a short circuit. But as long as we have an arc, would be arc length plus electrode extension equals the CTWD. Important to keep in mind because there's lots of mechanisms that relate to these subtleties we just discussed. And so in MIG, we protect the base metal using mostly using gases that would not react with the metal. Argon, for example, would not react with the metal, and we use pure argon in aluminum. We can also use CO2, but CO2 is not inert, right? But what happens is CO2, the molecule is bound like pretty tightly, so even if it ionizes and even if it dissociates, then it comes together and tends to leave not too much carbon and not too much oxygen. So CO2 is not inert, but that doesn't really contaminate the metal. Now, because it's not inert, this is the case when the Europeans say, ha, that's not MIG, because it's metal inert gas. That would be MAG, because it's metal active gas. Whatever, I'm gonna call MIG everything because the real name is GMAW. And whether we have, whether we have argon or whether we have, CO2, I'm going to call it, it's always GMAW, I'm gonna call it MIG. Now, something interesting about MIG is I mentioned that we want to protect the metal from the oxygen in the air. We want to protect the metal from the nitrogen in the air. However, look at this. A common blend for welding steels has 2% O2, 2% oxygen. So wasn't the story that we were trying to prevent the oxygen to come to the weld? And then we put it? It's kind of crazy, right? But there is a method to the madness. And what happens is that if we use pure oxygen with pure argon with when welding steels, the arc is kind of erratic. And if we use a little bit of oxygen, with a little bit of oxygen, then we create a little bit of local oxidation, and these oxides, especially in the cathode, stabilize the arc a lot. And the weld is a lot better. So typically for welding in steels, you're gonna see mixtures that are not pure. They would have a little bit of oxygen or a little bit of CO2. Filler metals. The filler metal is automatically fed, right, or semi-automatically fed, typically solid wire, but it can be a tube of wire. And if it is a tube of wire, we can put inside whatever we want. So if we put more metallic powders inside, it's what we call metal core arc welding. If we put fluxes inside, we call it flux core arc welding. And then we have something for which we have no name, but we have tried it in the lab, is what if instead of putting metal powders, and what if instead of putting fluxes inside the tubular wire, I put hard particles like tungsten carbide, which are neither metal nor fluxes. That exists, right? And that is used to repair overlays in the field. Has no name. Interesting. Some people call it the hardcore arc welding, whatever. Now, of course, because it all depends on, MIG welding depends on this consumable electrode, it will never be autogenous. Can be heterogeneous, can be homogeneous, but it's never going to be autogeneous. One interesting difference with TIG, and the difference is that if you remember TIG, we run at constant current. So we would have always the same intensity of the arc. But MIG we run at constant voltage. How interesting. So you might wonder, hey, didn't I want to keep the same intensity of the arc? And the answer is, yeah, of course you'd like to keep the same intensity of the arc. But there is something more important in MIG. Because the wire is being fed automatically by a machine that says so many inches per minute of wire, right, or so many meters per minute of wire go in, the main preoccupation in MIG is to keep a constant arc length, right? We don't want the machine to be crazy, giving us too much wire or too little wire. So because, as we're gonna see later, the voltage in MIG is given mostly by the voltage of the arc. If I say constant voltage, that is more or less like saying constant arc length. So in a MIG machine, the machine is going to give me more or less always the same arc length, more or less. And if I do crazy stuff, what changes is the current, right? And which I think is quite interesting. Typically, the electrode in MIG is positive, but you can have electrode negative too without major problems. If you have electrode negative, you have some trade-offs, which we'll discuss later when we talk about the physics of the arc, right? But you can. In gas tungsten arc welding, if you flip the polarity, you run the risk of melting your tungsten electrode. But in this case, MIG, if you flip the polarity, you tend to be still a happy person. For MIG is when the waveforms have been most powerful. So there are lots of waveforms for MIG machines, which we're going to discuss, start discussing today in the next couple slides. Sometimes you can have variable polarity, AC welding in MIG too. Those machines are not very common, they're expensive. We have them in the lab. It's in which you can change the polarity of the electrode as you pulse.
Gas metal arc welding uses a continuous solid wire electrode for the filler metal and a shielding gas to provide the desired arc characteristics and protect the molten weld metal from air. Gas metal arc welding is suitable for welding many types of joints of most any metal in all welding positions. The characteristics of the gas metal arc welding process are best described in terms of the three basic modes by which metal is transferred from the electrode to the work: the short-circuiting transfer, the globular transfer, and the spray transfer. The type of transfer is determined by a number of factors, the most significant including the magnitude and type of welding current, the electrode diameter, the composition of the electrode extension or length, and the type of shielding gas. The short-circuiting transfer mode encompasses the lowest range of welding currents and electrode diameters associated with gas metal arc welding. Metal is transferred from the electrode to the work only during intervals of controlled short circuits. The short-circuiting transfer mode is generally suited for joining thin sections, bridging large root openings, and for welding in all positions. The globular transfer mode is characterized by drop sizes with a diameter larger than that of the electrode. These molten drops are easily acted on by gravity, usually limiting successful transfer to the flat position. The spray transfer mode deposits small droplets of metal at rates of several hundred per second. Spray transfer requires high electric current and argon or argon-rich gas mixtures to shield the arc. Metal transfer is stable, directional, and virtually spatter-free.
All right. We'll discuss plenty about this metal transfer, but first of all, true or false? Who wants to venture an answer here? GMAW runs in CV. Yes, thank you so much. Thank you. Like we're totally on top of it. These questions might seem easy as we discuss. They're so important, and not everybody's aware of these things. There are good reasons for this, which we went into detail. So this video I just showed you talked about metal transfer. So as we melt the electrode, we have, like, say, two extreme possibilities. Few big droplets, the wire melts as few big droplets, or the wire melts as many small droplets, right? When we have few big droplets, we call it globular transfer. When we have many small droplets, we call it spray transfer. And these two differences here between projected spray and streaming spray essentially says how you go from these big droplets through small droplets to really small droplets. And we're going to discuss what these two subtleties are. That depends on current. Now, voltage, if I have low voltages, I would have short circuit. Now, before we get into some details, if I have power is current times voltage. So if I have low current and low voltage is the multiplication of two small numbers, low current on the left, low voltage at the bottom. So I would have low heat. And if I have high current and I have a high voltage, as the case of streaming spray, I would have high heat, right? So streaming spray would be good for deep penetration welds. Short circuit would be good for welds on sheet. So I have a question that says if the current in MIG is controlled by the arc length. And the answer is arc length affects the current. Yes. The most important variable to control current is the wire feed speed. I forgot to mention this earlier on, that in MIG, you set a voltage that is constant, but also you set another thing that is constant, that is the wire feed speed. You decide what wire feed speed you're gonna go, and the voltage will be constant, wire feed speed will be constant. And the current will adjust to whatever it needs to be. But typically, the biggest determinant of welding current is the wire feed speed. Okay, so I want to ask a question. Why do you think that short circuit is associated with low voltage? Oh, I have another question. Can spray transfer happen with CO2 gas? The answer is, I will discuss this in a minute, but the answer is typically no. And we'll get into more details maybe within the next couple slides. How about, what anybody wants to venture a guess why low voltage results in short circuit? Well, for the sake of time, I'm going to tell you the official answer. Voltage, every time we think about voltage in welding, in arc welding, we have to think the most important aspect of voltage is the arc length. Yes, yes, yes. Is about arc length. So if I have low voltage, I'm going to have a short arc, right? So here we have a suggestion about power, but actually with very small power, we can still have a plasma. I have seen welds done with 1 amp. I have seen it with my eyes. and less force is actually force doesn't play that much of a role in this case. So the short circuit happens because if we have lower and lower voltage, means shorter and shorter arc, until there is a voltage at which the arc is 0. We're gonna see how I don't need 0 volts to have a 0 arc. So that now this is a lot more. I have another question. Why when we have a short circuit, specifically where we want, if there is no electron beam? Okay, when we have a short circuit, and something, this question is helpful. When we have a short circuit, we're putting relatively little heat into the weld, but the short circuit breaks, and then we have an arc until the short circuit forms again. So the heat goes right between the electrode and the plate when there is an arc. And because they're so close, there are very few places to go. I'll show you videos later on that. So I'd like to hear if anybody has a theory why we go from globular to spray transfer as we increase the current. Here I have a suggestion for higher pulsation, but even if I have no pulses, I make this transition. If I have just constant current, I would have the same effect. So one of the hints is that with more current, we generate higher magnetic fields. And if we have higher magnetic fields, they interact with a higher current and they generate higher electromagnetic forces. We'll look into this later on, but the answer to why high current gives us this string spray, yes, right-hand rule, exactly. And the answer why we have a smaller and smaller droplets and eventually the string spray is because as we increase the current, electromagnetic forces squeeze out the electrode. It's called the pinch force. It's exactly the same physical mechanism that creates the plasma jet that can blow well your molten metal. So an interesting thing about welding is that although we can weld just because we have a torch in our hand, understanding the welding, the weld is super deep. And in the first class I mentioned, this big name is magnetohydrodynamics. That is what explains this transition from globular to spray. And we don't need to do big equations, but it's good to have in mind that it's just the intensity of the current that creates these electromagnetic forces that squeeze the electrode and make the droplets smaller. This is our time to stop, and we're gonna pick up here. We're pretty much on time, and we'll keep talking about metal transfer in detail next class. Thank you, everybody. If you have questions, you can send them to me by email. Let's stop here. Thanks.